welcome to Basics of Finite Element Analysis Part 2. Today is the last week of this last day of this fourth week, and what we will do today is develop the details of this two-dimensional one variable problem, and specifically we will do that in context of boundary value problems. So, first we will write down the model equation, the governing equation, and this is the equation we want to solve. Okay. So, the governing equation is del over del x a11 del u over del x plus a12 del u over del y, and there is a negative sign here, minus partial derivative with respect to y a21 del u over del x plus a22 del u over del y plus a00 times u minus f is equal to 0. So, this is the most general two-dimensional linear equation, partial differential equation, right, most general form in 2 dimensions. So, here a11, a12, a21, a22, a00 f are known functions. They are known functions of x and y. So, they can change with respect to x and y, but how they change we know that. So, that is the first thing. Second, u is unknown variable and it changes with x and y. So, our aim is to find what is our aim? It is to find this function u, x and y by integrating this equation A, and when we integrate this, so this is one equation with one variable, right. So, we should be able to solve for it, but the problem is when we integrate it, this is second order equation, it is second order equation, right. So, when we integrate it, we will get some additional entities. Now, because it is a partial, when we integrate a ordinary differential equation, then when we integrate it, we get integration constants. This is a partial differential equation. When we integrate a partial differential equation, what do we get? We get either functions of x or y or something, right. So, we will get additional functions. So, the unknown thing is not only u, but those also additional functions. So, those additional functions and u's will be calculated based on this equation A, which is one equation, and also additional boundary conditions which we have to apply. So, that is how we get the entire solution. So, that is important to understand. So, now here if a12 is equal to a21 is equal to a00 and this is equal to 0 and a11 is equal to a22 is equal to some function of a, x and y. So, this is, if this is the case, then if we put all this, then A becomes Poisson's equation, right. So, that is what we get. See, this term goes away, this term goes away, this term goes away, and this becomes A, then this equation then this equation, equation B is same as equation A, right. If we do the operations correctly, we can clearly show that equation B is same as equation A. Another thing I wanted to mention in this context is that for one dimensional equations, our domain was a line, right. So we broke this line into elements, and it was a straight line because we were talking about one dimensions. So the only thing which could vary was x, so the line could not bend or curve, it was a straight line. But in for 2-dimensional equations, the domain could be complicated, right. So this is my x, this is my y, the domain could be whatever shape as long as it does not change in the z direction. So domain is, this is a typical domain for 2D problems. So all of a sudden the complexity of the geometry becomes significantly large. It not only is changing, not only is there in 2 dimensions, but the shape could be not a rectangle or a square or a circle, but it could be some complicated shape. Okay, so that is there. So this equation, this is valid for this domain, and in 2 dimensions and 3 dimensions, and we can also use it in 1 dimension, this symbol is used for domain. If the domain is an element, then I can put a superscript, okay, omega e. But the symbol omega is a lot of times it is used to symbolize domain. Okay. Now we will develop a solution approach. Solution methodology for Poisson's equation. What was the first step for 1D problems? What did we do? Discretize. So the steps are the same. So the first step is we discretize domain into elements. The sequence of steps does not change, but the implementation of each step becomes fairly complicated compared to the 1-dimensional problem. So we discretize the domain into elements. Okay. Then we apply the equation for each element, because the equation is valid for all points in the domain. So we apply it to each element. So what was the second step we did in 1D problems? We developed a weak formulation. So then the next step is weak formulation of differential equation over an element. Okay. Because then we go down to the level of element, apply the equation on that element, multiply the error by a weight function, weaken the differentiability requirement for the variables, and that is how we get the weak formulation for a specific element. Then what do we do? No, before we integrate it, here we still have u. We represent primary variable so here primary variable is u in terms of what? Approximation functions. Right. Only once we assume these functions, then only we can integrate, right? Otherwise, how can we integrate? then we integrate to get element level. What kind of equations? Is it a partial differential equation? Is it a ordinary differential equation? Is it an algebraic equation? What kind of equations do we get when we integrate? We get linear algebraic equations of form what? Ke times u vector is equal to Fe. These are linear equations. This is known, K, F is known, U is not known. Then what do we do? So now we have equations for all individual elements. Then we do assembly. So we develop assembly level equations. And then we apply BCs and solve for U. Solve for U. So this is what we do. So the approach is same, but each step, at least first, almost all the steps are much more complicated. And if we can figure out how to do these steps for 2-dimensional systems, then we can easily use the same approach for 3-dimensional systems. But jumping from 1D to 2D involves significant increase in the level of complexity of the problem. So that is why it is important that we understand how 2D FEA works in a very rigorous way. So this is the methodology, and as we discussed here, the first step is that we discretize the domain into elements. Okay. So step 1, discretize domain to elements. So consider let us consider a circle for purposes of discussion, and I can discretize it like this as a lot of rectangles, right? I can discretize it, but we see that when I am discretizing it in terms of rectangles or quadrilaterals, there are some areas left which are not covered in my geometry. So this is the discretization error. This is the discretization error. We can discretize this domain into elements, and what we see something very fundamentally different in context of 2D is that the domain geometry is not necessarily accurately captured by all of our elements, right. So all these blue areas, they represent the discretization error of discrete error related to domain approximation, related to domain approximation. So, this is one additional error which comes into FEA for 2D and 3D cases. This error was not present in 1D case because there was no domain approximation error. So, this is important to understand. So, as we discretize, we have to make sure that our element size is reasonably small, so that the amount of this error introduced because of this is as small as possible. So, this is one thing. Now, I can discretize it not only in terms of rectangles, but I can also use triangles to domain, and so on and so forth. So, I can, so two very common topologies or elements which are used are triangles or a quadrilateral. Or a quadrilateral. So, we can use either only triangles or only quadrilaterals or a combination of those to discretize the domain. These triangles and quadrilaterals. So, in 1D problem, we could have a 2-noded linear element, this is linear element, or a 3-noded quadratic element, or a 4-noded cubic element, and so on and so forth. Similarly, we can have a 3-noded linear element. Okay. So, if you have 3 nodes for a triangle, then it is a linear element. You can have additional elements here, not elements, additional nodes here to get, and maybe in one in the center, to get a 7-noded quadratic element. And if I increase the number of nodes, then I can also have cubic or quartic or pentic and so on and so forth. So, I can have triangular elements of different varieties. So, whenever you do finite element analysis, you have to make sure that not only you decide what is the shape of your elements, but also what order these elements are. Are they linear or quadratic and so on and so forth. Okay. So, this is one thing. The same thing is true for quadratic elements also. A 4-noded quadratic element, quadrilateral element is linear in nature. But if I have 8 nodes or 9 nodes, 8 or 9, then this is quadratic in nature, and we will develop the mathematics for this, but at least at this stage you should be aware that this concept of linear, quadratic, cubic is not only valid for 1D elements, but it is valid for triangles, quadrilaterals, and if we go to 3D, it is for bricks, wedges, and so on and so forth. So, this is there. So, we have to make choice that what is the amount of triangles and quadrilaterals we want, and then the other thing is that these what is their order. Okay. So, if it is a quadratic element, it is a higher order element, linear is low order element, cubic is even higher order element. Okay. So, this is all language associated with it. So, some rules of when we are discretizing the geometry. First thing is that we have to make sure that domain approximation error is as low as possible. which essentially means that our element size should be small. The second thing is that suppose you have, let us say, a disk, and this disk is fixed at one end, and I am applying a point force here. Theoretically, if it is a point force, the stress here will be what? If I am applying a point force on a surface, what is theoretically the stress at that point? It will be infinite, because at that point there will be finite force divided by 0 area, infinite force. So, what that means is that stresses will be extremely large here. Now, in reality that does not happen, because material will yield and it will, but theoretically stresses will be very large here, but as you move, so stress is going to be very large here, but as you move away, stress will become less. As you move away, stress is going to become less, and when you come here, what will be the stress here at the point where it is rigidly fixed? Again, if it is fixed at just one point, all the reaction force will be witnessed by only one single point. So, again you will have a singular point here, and as you move away, stress will become less, okay, which means that in this region the gradient of stress, which is, so suppose the gradient of stress or even the gradient of u, displacement will also be very large here, right. So, gradient of stress and gradient of so stress in x and y directions at this point, it will be high or low? It will be high. So, in this region gradient of the solution is high, in this region, in the green region, gradient is not that high. So, if I am doing my discretization, we have to make sure that element size is small, and how small, you have to do several iterations on FEA and see whether you are getting the result in areas of high gradients. Because if you take large element, then you will not be able to capture the sharp variation of the gradient. So, you have to take small elements, which means that when you are meshing this, the purple area, you have to, in that area you have to take element size as very small. In green area you can take it, you can make it extremely small, but it will not give you some extra benefit. And the larger the number of elements, what does it mean? Computation time becomes large. So, when meshing is going on, especially in areas where you expect gradients to be high, you have to make sure that element size is small, and as you move away, you can gradually reduce it. So, that is the second thing. Third thing, transition from areas of low density of elements. See, in this area, in purple area, density of elements will be what? High, because element size is small. So, there will be lot of elements. So, number of elements per unit area will be high, and in green area it will be low. So, the transition, as you move from here you will have lot of elements, small elements, as you have in green you will have less number of elements, but large elements. So, this transition from areas of low density of elements to higher density areas should be gradual. This is important. otherwise you may have numerical errors which may be large. So, these are some rules. And then there is another very important thing. So, suppose you have a triangular element, and let us say it is a linear order element. So, it will have 3 nodes, okay. It will have 3 nodes. Now, suppose the adjacent element, let us say this is the adjacent element, and then there is a third element here. Actually, this will be better if I use rectangular elements. So, suppose there is a linear rectangular element. So, if it is a linear element, it has 4 nodes, and if in my mesh I have a quadratic element, I have a quadratic element. So, I have a linear element here, and I have this is linear element, that is a quadratic element, and suppose there is some element which connects these two, and I will not physically join them, but in reality they will be touching each other, but I have put some gap to make things clear. So, this is the connecting element, green is connecting element. Now, the question is, see, the linear element has 2 nodes at the common interface between green and red. The quadratic element has 3 nodes. If I use a linear element here, then this will be the situation. But then this node, when I am doing my assembly operation, I have to make sure that when there are common nodes, I have to, that I cannot do here at the interface of green and purple, right. And if I use a quadratic element, in case of green, the same problem will come between red and green, right. What do I do? Either I use in a mesh only linear elements or only quadratic elements, then there will not be any problem. But in a lot of cases, I want in some areas to get more information. So, I want linear quadratic elements or cubic elements in that area, and then other area probably solution is simpler. So, I can live with linear elements. But then what do I do? How do I connect linear elements with quadratic elements? This is important to understand. What do we do in that case? One option is you use an element called a transition element, and these are special elements where it is having some quadratic variation at one edge, and at the other edge it is linear variation. So, these are transition elements. So, use transition elements. To connect higher and lower order, elements. This is one thing we can do. There is another approach we can do. So, this is option 1. The other option could be, I still have linear here, and here I have quadratic, and then I can still, without using any fancy transition elements, I can still connect them with linear triangle. This is another linear triangle, and this is another linear triangle. This is another way to connect them. So, these are some of the important rules. for our how do you connect elements and how do you generate meshes. So, I think this is pretty much it for today and also for this week, and we will continue this discussion over next several days and probably close to 2 weeks, next 2 weeks, so that we develop a very good understanding of two-dimensional problems with one variable, because graduating from one variable to two variable is not that much complicated. So, that brings us to the closure for today, and thanks a lot, and we will meet once again next week. Thanks and have a great weekend.